Section 8.3 is about logarithmic functions, and we have four objectives. The first one is to graph logarithmic functions, then to convert from exponential equations to logarithmic equations, and vice versa, from logarithmic equations to exponential equations. Then we're going to solve some logarithmic equations, and then later on we find some common logarithms on your calculator. So the first objective is graphing logarithmic functions. So first of all is a definition of a logarithm. This expression reads the logarithm base 2 of x, or log base 2 of x, means the power to which we raise 2 to get the number x. In other words, the logarithm is an exponent, the power to which we raise 2 to get x, with 2 being the base. Now graphically it looks like this. The first graph is the graph of f of x equals 2 to the x, this one here. Here is the line y equals x, and across the line we rotate the f of x equals 2 to the x, and that is log base 2 of x. That's a graph of log base 2 of x. So that is the inverse of f of x equals 2 to the x. So these functions are inverses of each other. That's the important takeaway from this graph. It's a good one to remember what it looks like, because everything else is just a change, or it changes over. Like we could have a different base. As we'll see later on, the base could be 3, or the number e, or 10, common logarithms, etc. So the base is not always 2. It's just one example that the base is 2. So here are more details. If f of x equals 2 to the x, then f inverse of x is the log base 2 of x. Notice that f inverse of 8 is a log base 2 of 8, and that's equal to 3, because 3 is a power to which we raise 2 to get 8. In other words, 2 to the third equals 8. So again, remember the logarithm is really an exponent to the base. In this case, the base is 2. Although expressions like log base 2 of 13 can only be approximated, remember that log base 2 of 13 represents the power to which we raise 2 to get 13. So 2 to log base 2 of 13 equals 13. In other words, that would be a number between 3 and 4, because 2 to the third is 8, and 2 to the fourth is 16. And so to get 13, it's going to be between 3 and 4. So then the first objective is to write the meaning of log base 2 of 64, and then find the log base 2 of 64. So the meaning of log base 2 of 64 is the power to which we raise 2 to get 64. And since 2 to the 6 equals 64, log base 2 of 64 equals 6. So here's some more on the definition of logarithms. The inverse of f of x equals a to the x is given by f inverse of x equals to log base a of x. We read this expression as a logarithm base a of x. We define y equals log base a of x as a number, as that number y, such that a to the y equals x, where x is greater than 0 and a is a positive constant other than 1. So that is the definition you want to keep in mind for this section in particular. And again, here are the graphs the function f of x equals a to the x, or y equals a to the x, where a is greater than 1. And here's the line y equals x, and here's the inverse. F inverse of x equals log base a of x, or y equals log base a of x with a greater than 1. As mentioned before, it is helpful in dealing with logarithmic functions to remember that the logarithm of a number is an exponent. For instance, log base a of x is the exponent y in x equals a to the y. Keep thinking, the logarithm base a of a number x is a power to which a must be raised in order to get x. So this definition is something you may want to remember and perhaps even memorize. Here are the complete definitions. The exponential function y equals a to the x, or f of x equals a to the x, with a greater than 0 and a not equal to 1. Where the domain is a set of real numbers and the range is a set of positive numbers. Then the inverse, the logarithmic function, is equal to x equals a to the y, or f inverse of x equals log base a of x, with a greater than 0 and a not equal to 1. Where the range is a set of real numbers and the domain is a set of positive numbers. In other words, x has to be a positive number. So as an exercise, let's find the graph of y equals f of x equals log base 3 of x. So let's create a table of values in ordered pairs. So here's our table of values in ordered pairs, and here's the graph of y equals f of x equals log base 3 of x. Next, we'll use the definitions of logarithms to convert from exponential equations to logarithmic equations. So if y equals log base a of x, then a to the y equals x, or a to the y equals x means y is the log base a of x. So be sure to memorize this relationship. It's probably the most important definition in the chapter. Often this definition will be a justification for a proof or a procedure that we're considering. So this is something you definitely want to memorize, otherwise it'll be difficult to do the exercises, among other things. So here we have to convert to a logarithmic equation. Remembering the definition, we simply write this as 0 equals log base 6 of 1. It's 6 here. Similarly, in the next exercise, 10 to the minus 3 equals 0.001. So that means minus 3 equals the log base 10 of 0.001. For this exercise number 5, it means 0.25 equals the log base 16 of 2. And here, in the general sense, it means that t equals the log base m of p. So here it's the reverse. So this means 2 to the 5th power equals 32. or in this case base is 10, the exponent is 3, so 10 to the third equals 1000. Or a to the 7th equals q. And for number 10, t to the x equals m. Based on the definition of a logarithm, we can solve certain logarithmic equations. For instance, solve the log base 10 of x equals 4. So what that means, 10 to the 4 equals x, and so x equals 10,000. Because 10 to the 4th equals 10,000. Number 12, we have the log base x of 81 equals 4. So what that means is that x to the 4th equals 81. And since 81 is equal to 3 to the 4th, since the exponents are the same, that means that x equals 3. Similarly, number 13 implies that 2 to the negative 2 equals x, and 2 to the minus 2 equals 2 to the minus 2 is equal to 1 divided by 2 squared, or 1/4. So x equals 1/4. So here's a guided solution. The log base 10 of 10,000. So here we set the log base 10 of 10,000 equal to x. That means 10 to the x. 10 to the x power equals 10,000. And that means 10 to the 4th. 10,000 can be written as 10 to the 4th power. Therefore, since the bases are the same, the exponents must be the same. Therefore, x equals 4. Similarly, for number 15, we let the log base 10 of 0.0001 equals x. So that means 10 to the x equals 0.0001. And so that can be written as 10 to the minus 4. Comparing exponents, that tells us that x equals negative 4. Or we can rewrite this as log base 10 of 0.0001 equals minus 4. Similarly, for the next exercise, we can write log base 7 of 1 as the log base 7 of 1 as equal to x. And so that implies that 7 to the x equals 1, or we can write 1 as 7 to the 0 power, which implies that x equals 0. So therefore, log base 7 of 1 equals 0. Next are two important identities. The first one is the logarithm of 1. For any base a, the logarithm base a of 1 equals 0. In other words, the logarithm base a of 1 is always equal to 0. It doesn't matter what the base is. Similarly, the logarithm of any base a, the logarithm base a of a is always equal to 1. So these are two very important identities, and it would be a good idea to memorize them. Let's apply these identities to the next exercises. So log base 3 of 1 equals 0, because the log of 1 to any base is 0. Similarly, the log base 3 of 3 equals 1. And the log base c of c is equal to 1. And the log base c of 1 equals 0. Next, we'll be discussing common logarithms and how to find them on the calculator. And so the base 10 logarithms are called common logarithms. Before calculators became widely available, common logarithms were used extensively to do complicated calculations. And so the abbreviation log, with no base written, is used for the common logarithm base 10. In other words, when you see that expression, it means base 10 is implied. Log of 29 really means log base 10 of 29. So this is an important thing to memorize. Log of a simply means log of base 10, log to base 10 of a. So to find the common logarithm to 4 decimal places on a scientific calculator or graphing calculator, we do the following. We input the number 78,235.4 in our calculators and press the log 10 key, and that'll give us the logarithm, the common logarithm, that is. So here I input the number 78,235.4 in my calculator, and so now I press the log base 10, and so here's the answer, 4.8934 to 4 decimal places. Let's just think about the answer to see if that makes sense. 78,235.4 is between 10,000 and 100,000, and the log of 10,000, base 10, would be 4, and log base 10 of 100,000 would be 5. So the number, the answer should be between 4 and 5, and it certainly is, and it's closer to 5 than to 4, because 78,000 is closer to 100,000 is to 10,000. So you can always compare the answers and see if they make sense. For the next exercise, I put in the number 0.000309, and again I press the log 10 key, and here's the answer. Oops, what went wrong here? So minus 4.5100 is the answer for the next exercise. Minus 4.5100. Now for number 23, the answer does not exist as a real number, because remember, the domain of the logarithmic function is a set of positive numbers. So this one does not exist as a real number. So here, number 24 asks us to find the log of 1,000 and the log of 10,000. Remember, this is base 10. So the log of 1,000 equals 3, because 10 to the third equals 1,000. Similarly, the log of 10,000 equals 4, because 10 to the fourth equals 10,000. And between what two whole numbers is a log of 9,874? Well, 9,874 is between 1,000 and 10,000, so it must be between 3 and 4. So between 3 and 4. And then using a calculator to approximate the log of 9,874 and round it to 4 decimal places. So the log of 9,874 base 10 is equal to 3.9945 rounded to 4 decimal places. For the next exercise, we have to complete the table to express each number in the first column as a power of 10. Round each exponent to the nearest 10,000, so it means 4 decimals. So for the number 8, so we input 8 in the calculator, and then we look up the logarithm, 0.90308. So in other words, it would be 10 to the 0.9031. And for next number, 947, we know that it's a power of 10 between 2 and 3, because the 947 is between 10 squared, which means the logarithm is 2, and 10 to the third for 1,000, so between 3 and 2. So let's do that. So 947, the logarithm of that is 2.9763. So it would be 10 to the 2.9763. And in a similar way, we complete the table also with the other numbers. 634,567. The log base 10 is 5.8024. So it's 10 to the 5.8025, rounded to 4 decimals. And so we do the same thing for all the other numbers. For exercise number 26, we input 4.8934 rather, and then we use the 10 to the x power key, and they'll give us 234.8042 to 4 decimal places. I hope you will attempt these exercises on your own with a calculator, and all of them, number 25 and 26, just to learn a little bit more hands-on. And this concludes section 8.3.